So if you remember from our practical then, we took 3 blocks, 3 cylinders, we provided them with some heat energy via an electrical immersion heater, and we measured the temperature as we supplied them with heat energy. So as the temperature increased, or as we added more and more energy, the temperature increased. We were just measuring this over a period of time, and now is the time that we can figure out just how much energy that we were putting into these blocks. Okay, now let's start by looking at the immersion heater. Now the immersion heater, we supplied it with 12 volts of potential difference across the heater and 4.15 amps through the heater. Now what I'm going to do is just use this equation. I'm going to use P equals IV. That's power is equal to a current times by potential difference, or current times voltage, to measure the power that we were supplying the block with. In other words, how much energy were we giving the block every second? Now, this is electrical power. This is an equation for electrical power. We were using an electrical immersion heater, so it works here. Right, let's take 4.15 and multiply it by 12. Just get a calculator up. I should have done this before I started recording. Calculator. So I'm going to just do this on my computer. 12 times by 4.15. Okay, I'm getting a power of 49.8. So that equals 49.8, and the power is in watts. It's in joules per second, which is also, you can just say watts. Watts is better to say here. What I might do, just for the sake of convenience, is I might just say that they're a 50 watt. I might just call it a 50 watt heater, and then we can probably make the same assumption for all 3. I know the current was slightly different for all 3 of them, but we can just say that they're 50 watt heaters. Okay. There are other sources of error in our investigation that we'll talk about later that will be more significant than a 0.2 watt error on power. But we can talk about those later as well. Now, energy transferred then. So so we've got the power, which we've got as 50 watts. Now we need to figure out the energy transferred. Well, what do we have? We've got time and we've got temperature. Temperature is not going to tell us anything about energy, but we have power and we have time. So if you remember this equation, power more generally, power is equal to the amount of energy that you transfer into something, or the amount of work you do, divided by time. So power is just energy divided by time. We can rearrange that. P times T will give us E. Okay, so power times by time, that's 50 watts times by whatever time we've got, is going to equal the energy that we transfer into the block. So let's do this for all of these readings. Now, if our power is 50 watts, then over 0 seconds we're going to have transferred no power, no energy at all into the block. So 50 watts, that's 50 joules per second. How many joules are we going to transfer in 120 seconds? So 50 times 120. 50 times 120. That's going to give us 6,000 joules. Okay, so in 2 minutes we transfer about 6 kilojoules into the block. And then we do the same again. So 240. This time we're going to times it by 50 again. We get 12,000. Okay, and you can see that it's just going to go every 2 minutes. We transfer about 6,000 joules in. So let's just keep going up. So this is going to be 18,000. This is going to be 24,000. And this is going to be 30,000. Okay, so we've thrown 30 kilojoules, or 30,000 joules, into the block and caused its temperature to increase to 80.4 degrees. Right, now in order to get the graph that we're going to draw, I would say that it's probably best to put energy transferred on the bottom. So we were supplying the block with energy and measuring the temperature increase. So put the thing that we're going to measure on the y-axis, and we can and we can then figure out a gradient calculation from that. I'm going to go ahead and pause the video and quickly draw the graph. I'll see you in a moment. Right, so back again with the graph then. You can see that I've plotted a straight line of best fit through the points. Now it's not gone through the origin. Okay, it's gone through, we can see where it's gone through. It's gone through 26.0, so that was the starting temperature of the block, which makes sense. It's increased its temperature all the way up to 80.4. Now we're going to use this equation to calculate the specific heat capacity. So the energy that you transfer into a block, that's delta E, the change in energy that the block has, is going to be equal to the mass of the block multiplied by its specific heat capacity, which we represent with the letter C, multiplied by its change in temperature, which we represent with a delta theta. Okay, so these delta symbols here, these triangles, those both mean change in. Okay, so that's change in energy and change in temperature. So they are sort of separate. Yeah, they're together. I mean, okay. So they're both single quantities. Okay, the delta doesn't represent anything other than change in. So it's change in energy, change in temperature. Okay. So specific heat capacity then, remember, is the amount of energy, yeah, that you need in order to raise the temperature of 1 kilogram of a block by 1 degree C. That's the specific heat capacity, and it's measured in a unit called joules per kilogram per Kelvin, or per degree C in our case. Okay, so joules per kilogram per Kelvin. Sorry, I should remove that slash there, and it'll be more accurate. There we go. Right. So first thing we're going to do then to figure out this quantity here, C, is take the gradient of the graph. Now the gradient of the graph is just the change in the y divided by the change in the x. So what is the change in y? So the y-axis is temperature. So the change in y is the change in temperature. Okay, the change in temperature, which is this bit of the equation. The change in x, okay, is change in energy transferred. So it's this bit of the equation here. Okay, if I take as large as possible the gradient as I can, so we're going to start all the way down here, and we're going to do a gradient calculation all the way up to here. Okay, so the biggest gradient we can. I'm going to draw this triangle. This side represents change in y. Okay, in other words, the change in temperature, delta E. Sorry, delta theta, not delta E. My mistake. This side length at the bottom here is delta x, which represents change in energy, delta E. So we take change in y divided by change in x. That's change in delta. So what does it start at? Well, it started at 26.0 and it finished at 80.4. So a quick calculation to find the difference between them. So 80.4 minus 26.6. You get 26.0. You get 54. Okay, so 54 degrees change in temperature. Okay, on the bottom here, change in energy. Well, we started at 0 and we've gone up to 30,000. So this is just going to be 30,000. Okay, so let's take the two. Let's divide them together. That's delta theta divided by delta E. We get what do we get? So we get 54 divided by 30,000. Okay, and that's going to give us 0.0018. Okay, now what quantity does this represent? So let's rearrange this equation to get C. So what I can do is I'm going to move M. You can only move these things diagonally. So I'm going to move M down here. I'm also going to move delta theta down here. So I end up with an equation that looks like this: delta E divided by M delta theta is equal to C. So we've already got this bit here, except instead of getting delta, here we've got delta theta over delta E, we want delta E over delta theta. So all you need to do really is reciprocate this, and you can do that by just taking 1 and dividing it by what you got, so 0.0018. Okay, by doing that you're basically turning it from delta theta over delta E to delta E over delta theta, which is what we want. Okay, so let's reciprocate it. 1 divided by 0.0018, you get 550, let's just round it to 556. Okay, now what we need to do, we've still got the m on the bottom, so we've got to divide it by the mass of the block. The mass of the block was 1 kilogram, so 556 divided by 1 gives you 556. So there is our specific heat capacity, 556 joules per kilogram per degree C. Okay. Now the actual value for the specific heat capacity of copper is, I've got it up here, I'm getting 376 or 377. Okay, so we are some way off here. This here is much higher than we expect. Okay, it's not quite double, but almost double. So what does this imply? Well, somewhere, so we've got a higher specific heat capacity than what we expect. So something is happening here. We have made one crucial assumption in our calculation. We have assumed that every bit of this energy that we put into the block is going into heating up the block and nothing else. We've assumed that it's totally isolated and insulated from the table, from the air around it, and that the heater is transferring 100% of the energy that we put into it into heat energy. That's not a particularly accurate assumption to make. We can't really assume that some of the heat is not being lost to the air, because probably quite a significant amount will be. Likewise, a lot of it will be transferred to the table beneath it. But what we did do to try and minimise that was we put it on a heat-proof mat, which would have helped a little bit, but not a significant amount. So this is actually higher than we expect because we've made that assumption, because we've made an inaccurate assumption that none of the energy is going to be lost to the environment. Right, so what I want you to do now is go back to the video, record the temperatures for the aluminium block, record the temperatures for the steel or the copper, the iron block, and then do exactly the same process as I've done here, and work out the specific heat capacity of those blocks. Use the internet, find an actual value, and see what you get. See how accurate you get. See you in the next video.